This is the last section of this chapter, and it would be so nice to start this course here because it is the most interesting. But you need all that background from chapter 1, chapter 2, and chapter 3, as well as what we've done in chapter 4 to be able to understand what's going on. So when we do the stoichiometry, we have a solution that has an accurately known concentration that we call a standard, and it's added to another solution of an unknown concentration. And those would be the techniques on the right. All the calculations involve stoichiometry from chapter 3, and we're going to do 3 different examples: neutralization, precipitation, and redox. Because as you know, as we've gone through our pandemic, protocols are very important in the real world so that you can look at accuracy and precision. So let's move to the first one. Neutralization, or an acid-base titration. We cover this heavily. You do a lot of calculations in 1220. But for now, moles of acid equals moles of base. And we want to know how many mils of sodium hydroxide are required to reach the equivalence point, and you'll learn that's pH 7 for a strong acid, strong base, if we are using 20 mils of 0.120 molar nitric acid. So again, acid plus base makes water and a salt, but all we're concerned about here is what are going on with the reactants. So what I did is I spread it out. I do not enjoy presenting it in this manner, but it works for having to record. So again, at the equivalence point, moles of acid, which in this case are HNO3, are going to equal moles of base, which is sodium hydroxide. And what I've done is the moles of acid, volume of acid equals moles of base times volume of base. Sometimes you'll see a problem like this, and I guess you should really just jump up and down because it's really, really easy. I hate to use the words plug and chug, but that's exactly what happened. And we did this in a titration problem, standalone. It would take 30 mils of base in order to do this titration, okay? Now, notice that our acid and base are in a 1-to-1. So what I did here is I left some holes. What if I had 0.120 moles of HNO3 and I had 0.0200 liters of HNO3? I'm writing a 1 sodium hydroxide to a 1 acid. But that might be different if I have, say, calcium hydroxide. I have to make that adjustment. And then my third part is just what we did earlier, where we're using our molarity of base. And what we will come up with is the exact same answer. We will come up with 0.0300 liters. Either method gives you the same answer, but please be careful and look at the stoichiometry between the acid and base. Again, I wish I could write everything down, but it's just not working, all right? So in Columbus, we monitor the water. In fact, they monitor it 2 blocks from my house at a UDF, which I did not know until my friend who works there told me. But we want to know how much chloride is in the drinking water so the bacteria is contained. And there is a standard solution of known concentration that has a silver ion. It reacts with an unknown concentration of chloride ion in the water samples that they take, and it produces silver chloride, the solid. So just like with a titration at the equivalence point, for this precipitation, moles of the cation are going to equal moles of the anion. Same principle, same method. What I have here is an actual sample that they would take here in Columbus. They would use a 20 mil sample of silver cation, 0.100 molar. And if you notice, moles per liter of solution times liters of solution give you your moles of silver cation. Well, at the equivalence point, the moles of the Ag plus must be equal to the moles of the Cl minus. Now, I'll be honest, I'm a chemist, I've done it for a long time, but when I look at this next calculation, I have a hard time. It tells me I have this many moles of chloride ion, and what I do is I use the atomic weight of chlorine. I don't know why it bothers me, but what it does is it gives me the grams of chloride ion. So what you have to do is account for how big your sample is. Now, here is the sample size, 10 gram sample, because what we do is we put our grams of chloride minus divided by our grams of our sample. And it's very rare to measure something and get 10.00. So I'll be saying some things in the Zoom because it's not recorded, but I'm going to leave it at this for now. And that tells us we have 0.710% chloride ion, and they compare it to different areas in Columbus to adjust what they need to do to purify the water. I come from industry, so to me this is interesting. It may bore you to tears, but really you do drink water, okay? My last sample is not to scare you, all right? You could do this problem as long as you were given the balanced chemical equation. There's no reason you could not do this without that equation. So it says a sample of blood plasma is titrated with an acidic potassium dichromate solution, and it results in the production of Cr3 plus and carbon dioxide. I'll let you pause and look at all the different pieces that are sitting in this equation. They want to know what is the mass percent alcohol in the blood, otherwise known as the BAC or blood alcohol content, if we have a 30-gram sample of blood plasma. So again, chloride, we had a sample. We didn't quite do it that way for a titration, but this does match the precipitation. Notice what I did. Here is the dichromate solution ion. Here is the ethanol that is in the bloodstream, and it's a balanced equation that you would receive. Notice the 2 and notice the 3. You can do this problem. Here is our molarity of the dichromate solution, accurately known. Here is the amount that it took to titrate. This is the stoichiometric ratio that we've been pushing since chapter 3. So you don't even have to know the chemistry. You just need to know those stoichiometric ratios. And then the last part is the molecular weight of the ethanol. It turns out to be 0.0429 grams of ethanol, and just like in the last problem, we would look for the mass percent ethanol in the blood plasma. There is our 0.0429 grams, there is the mass of our sample, and we would come up with a BAC of 0.14. So I like this problem because, not that I want you to do these things, but you can actually relate to what it is. For the last slide, I have these must-knows. If you're preparing for the exam, choosing Alex is going to let you know if you understand and can do this. But I want to mention things. You have to know the difference between an electrolyte and a non-electrolyte, cold. I would suggest you learn the solubility of ionic compounds. It increases the speed at which you can have solve problems. Please know about these 3 types of equations, be able to write them and recognize them. Memorize your 7 strong acids and 7 strong bases because any other acid is weak, any other base is weak. Oxidation behavior of metals in acid solution, we will have a problem where you do not get an activity series, but you're able to logically figure out what is going on. And then all the calculations. I know some of you despise math, but even if you want to practice medicine, I listen to my daughter-in-law who's a physician, and you still have to do it. So, just suck it up and let's see what we can do. Please, please, please ask questions. I know I say that at the end of each of these. I cannot remove my personality from these YouTube videos, and I just wish we could meet in class in person.